This is our presentation for the Michigan Space Grant Consortium Conference. This is on magnetic nanoparticle-based motion sensing for Grand Valley State University. My name is Chase Tuttle. I'm a senior at Grand Valley. I'm a mechanical engineering major, and I was an undergraduate fellowship awardee.
My name is Jackson Brennecke. I'm a graduate student here at Grand Valley State University studying electrical and computer engineering. We'd also like to mention our faculty advisor, Dr. Brian Krug. So this research picks up on some previous research done by Dr. Brian Krug. The principle of this research is based on a novel sensing technology based around ferrite nanoparticles. The way this works is by supplying alternating, rotating magnetic fields that cause the nanoparticles to spin. Once the nanoparticles are spinning, we're able to induce a magnetic field on them and then sense the response that they produce.
With the previous experimental setup, we used a stepper motor to change the direction of the nanoparticles and the Arduinos in order to sense the current coming off of them and for data acquisition. Currently, we are using this turntable, which was awarded through the grant, and the controller behind it corresponds to the software included, which controls the angle of the turntable, which can manipulate our nanoparticles to a very specific degree and provide very accurate position feedback. All right, this is our Aerotech rotational table and the respective controller. The rotational table is guided by the software right here, and the program was written by Jackson, and that allows us to control exactly what angle the rotational table goes to and what speed. Now our circuit over here takes an AC input and it is amplified, and then this amplified signal is sent through these two current sensors. Now one of these signals is offset with a phase shift by 90 degrees, as you can see on the oscilloscope, and then that is sent to the nanoparticle sensor. Now as the nanoparticle sensor rotates around, the DC output from these two current sensors will change. This DC output is then sensed by these two DMMs right here. One of the DMM's outputs is sent directly to Excel, so it can record the values which are output by our sensor in real time. While it's being graphed.
So the first part of the research was improving the experimental test setup to get more accurate data, and then the second part that I worked on was further developing the theory behind it and trying to get a better understanding of the response of the system. So rather than just looking at the magnitude, we're looking at the full vector response, which helps us to determine the angle of tilt with a greater degree of accuracy than was previously possible. The research I've been doing has primarily been, as I mentioned, theory-based and then simulation-based as well, using various tools such as MATLAB. Our goals moving forward are to complete the data collection and then compare the collected empirical data to the developed theory and simulations to try and get a better understanding of the accuracy of this technology and to evaluate the viability.